Okay, we'll get started with our reading quiz for today. And our first question is in regards to anelasticity. So anelasticity is A, when rubber bands lose their elasticity. B, a reduction in cross-sectional area upon tensile loading. C, a recoverable strain that does not occur immediately. Or D, the onset of plastic deformation. Okay, answers in. We're going to go to the next question. It's technically still, with like 30 more seconds. We started a little bit early on this one. Okay, if you're just coming in, hurry and get an answer in. A, B, C, or D, you got 25% chance. We're going to wrap it up though. Okay, I'm going to end this one. Okay, so C or D, the answer is C. C. So we're going to talk about this today. This leads to viscoelastic behavior. So basically, when you apply a load, it's still elastic, means it's reversible, but you don't see the sort of strain immediately. It slowly approaches that, and that leads to really interesting properties. Okay, next question is, necking is A, something your parents warned you about in high school, B, the type of plastic deformation, C, localized reduction in cross-sectional area, or D, all of the above. Okay, A, B, C, or D, answers in. Okay, we're going to wrap this one up. It is all of the above. I made all of these worth a point, so don't panic. They're all worth a point. But it is all the above. We'll come to necking later today. Because your parents may have never warned you. They may have encouraged you. I don't know. Okay, the area under the stress-strain curve in the elastic region is known as the modulus of resilience, toughness, Poisson's ratio, or shear modulus. Area under the curve.
Did you catch my logic for that one?
Didn't hear it.
I know that Young's modulus is the second derivative, since this is a derivative. Might also be a modulus.
Okay. Not the worst logic. Okay, we're going to wrap this one up. The area under the curve.
Oh, wait, this is the new derivative.
is, good guess on toughness. It's actually modulus of resilience. We'll talk about that later today. Okay, so we left off last time saying that when you apply stress to something, you see a strain, right? And how much strain you observe, there's a constant of proportionality called E, Young's modulus. We talked about this first or second day of class. Now we're getting back to it again, right? Since epsilon, our strain, is unitless, and you're applying stress on one side equals this modulus of elasticity multiplied by the strain, then the modulus of elasticity has to have the same units as your stress, right? So if this is in megapascals, it's also in some sort of megapascals or gigapascals, right? It has to be the same type of unit, okay? And they're proportional. This is basically saying it's a linear relationship, right? It doesn't have to be. There are exceptions to this. There's non-linear behavior, and we'll show that in a moment. For most things, it is generally linear, though, right? And it'll be linear up into a point, and after that point, you see the onset of not elastic deformation, but plastic deformation, which we've described before as non-reversible. It's permanent deformation, right? So our next clicker question is, in these pictures you see here, we're going to ask which one of these is the ceramic. Oh gosh, let me kill the timer. Forget when I put timers on these things. Okay, let me move that. Which of these materials in the stress strain figure on the left is the ceramic? Is it blue, red, green, or purple? And if you're colorblind, the steepest slope is blue, then red, then green, followed by purple. So blue, red, green, purple. Okay, so play the countdown. Answers in. Okay, what do we think? Okay, overwhelmingly correct answer. The blue is the ceramic. How do we know that? Because ceramics are generally the highest modulus because they're the strongest bonds. They have the deepest potential well. That leads to this high slope in the force versus interatomic distance. So there really takes a lot of force to get just a little shifting of those atoms. So that's the steepest slope, therefore that's your ceramic. Let's go to our next one. Which material would be the polymer? Again, that's blue, red, green, or purple. So which one is the polymer?
The second has like match.
Yeah. By the same logic, the thing that's the most what we call compliant, or the least stiff material, when you apply a load to it, it stretches easily. It's going to be your polymer. Therefore, the one that takes the lowest slope in terms of stress versus strain. Okay? All right. So as I said, usually this region here in the elastic region is going to be linear. It doesn't have to be. Some materials, including some important ones like concrete and cement, some cast irons, they're non-linear, meaning it doesn't have to be this linear thing. It can actually bend, but it'll still be recoverable. Right? That's non-permanent deformation. It'll go back to where it was initially, right? For most materials, when it bends, when you see a bend in this curve right there, that typically we're talking about the onset of plastic deformation. Yeah, Spencer?
That other graph, what is the green one?
Green we'll talk about in a minute. So you see something interesting happening here where it sort of jogs down and then it gets up.
Yeah.
So there's some sort of event that could be a composite where, let's say it's a fiber reinforced composite, and as soon as you're loading it, maybe the fibers are taking most of the load, and that might be like fiberglass. But once those break or become dislodged, now that load would shift to the matrix. So that could be one thing. More likely, this is a type of metal where it undergoes. We're going to talk about it. I forget the name of it. It's like a yield event or something where it does this initial jog, but then it keeps getting harder. We're going to come back to that exact scenario in just in a few moments. So this plot, thought we lost our pen. This plot here, grab the color, at the onset of non-elastic behavior, sometimes this is called the proportional limit, right? But it's sometimes tricky to say. Where exactly is it starting, right? And so just so that we're all on the same page in this field and talking about when plastic deformation occurs, what they normally do is they define a specific strain as the yield strength, right? So the strain is this, right? When you load it up to this stress right there, right? So you're right here, and then you let that stress off, it's going to relax and it's going to go back with a specific slope, and that slope is going to be whatever your initial slope was, right? And if it goes back and you're left with 0.002 for your strain, or 0.2%, that by definition is the yield strength, right? Because it's hard. It's hard to say exactly where this is happening at. We all just decide, okay, what we're going to define as yield strength is when you load it up to something and you have a permanent strain of 0.2 strain, okay? 0.2%. Let's see, I can skip that. I'm going to skip this because we already talked about it. So what are some typical values for elastic modulus? In general, ceramic is higher than metals, and that's higher than polymers. And the numbers that you can expect, for ceramic, it might be anywhere around between 50 up to maybe 400 gigapascals, so extremely stiff materials, whereas polymers can be less than 1 gigapascal. And metals are going to be somewhere in between, maybe 100, maybe 10 gigapascals, somewhere in that range, right? Okay, when you heat things up, you increase them up in temperature, they tend to, and this is probably common sense, they tend to become less stiff. They tend to become more compliant, right? So moduli will usually decrease with temperature. That's not always the case. Some things, like it might be a polymer where it's continuing to crystallize or form bonds, and all it needed was a little bit of temperature, and that made it more stiff, right? Because it formed more bonds. But most materials don't behave that way. They get more compliant as you heat them up. Anybody who started with, like, say, honey in the winter, right? Honey is very, very brittle and hard when it's cold. You heat it up and it becomes more and more compliant, and it'll actually begin to flow. So honey is something where we observe viscoelastic behavior, which we're going to get to in just a minute. Okay, shear stress and shear strain. We talked about shear stress again. So if I took this table and I press straight down on it, I'm applying compressive stress. But if I take it instead, I'm pushing along this, I'm using the friction, and I'm pressing, and the force, while there is a component that's pressing down, right? There's also a component that's pressing parallel to this face. So I would be shearing this table a little bit, right? So shear is a different type of stress we talked about in the video on Friday. And just like stress, if I apply stress and the constant of proportionality is Young's modulus, that tells me how much strain and compression occurs. There's another constant of proportionality when you're talking about shear, when you're sort of applying this force parallel to the face. We call that G, the shear modulus, right? So again, just like strain, now we're talking about shear strain. When you apply shear stress, you can produce a shear strain, and the constant of proportionality is now G, the shear modulus. Okay, anelasticity. When you apply a load, right? Let's say I took this table and I lean on it like this. So my load is pressing straight down on it. It's gonna shrink a little bit, right, at first. But if that keeps on shrinking as a function of time, it sort of slowly happens, that's called anelasticity, and it leads to some really interesting properties. In fact, there's a really cool paper, I forget where this came out. Was it Wired or where was it? Gizmodo? Let's find out. A group out of Georgia Tech is doing this, and it's pretty awesome.
This brown leafy material looks like mud, but it's a lot.
Really loud. So, fire ants. Anybody see these pictures from Hurricane Harvey that just happened? Down in Texas, fire ants are everywhere down there. And people were taking pictures of these lumps of what just looked this brown sort of mass, and you got closer, and it was like a giant horde of fire ants, which is possibly the most horrifying thing you ever heard of, right? So how do they do that? This group in Georgia Tech is actually studying them, and they realize that how it happens is their legs connect together, right? I'm not going to show the whole video, but their tiny little legs can link together, and by doing so, plus like the properties of their surface energies of their skin versus the water actually makes them repel water. So by clumping together, they can actually prevent the whole thing from sinking. Moreover, they actually show some interesting videos where they actually compress it underwater, and air gets trapped inside so they don't drown. So it's just really hard to kill these things because evolutionarily they grew up in places where flooding was common, so they evolved a way to prevent that. So this group in Georgia Tech is studying them as if they were an engineering material, which is kind of neat. And they basically said, well, we can take polymers and we can link them together. And what if you start to understand how things link together? Could you make materials that start to act like fire ants and have some of their interesting properties? And the one I wanted to show you, I think it's right around here. Yeah, right around here. Viscoelasticity. By the way, they've done like everything to these ants. It's kind of horrific. Like if you can think of it, they've done it.
They made mathematical models to describe the ant's behavior, and they characterized the impulse as a viscoelastic material, which means they have properties of both.
They're solid and they're elastic. So, for example, by taking a spring, you squish it, it'll get you back.
But they also act like a viscous fluid when under stress, breaking and reforming with specific energies in a way that resembles a slow flow.
And that's basically how fluids work. They have very small, weak bonds everywhere, like water has hydrogen bonds. It's because the bonds can break it and you feel really easily.
Okay, there's more we could go on to. Let's shift back to viscoelastics. So again, viscoelastics, and we'll show this in a moment. But if you were to apply a stress, let's plot strain up here as a function of time. If you applied a stress that was instantaneous, then you would expect an instantaneous elastic response, right? So as soon as you apply the stress, it's going to be like that. When you take the stress away, you expect it to go away immediately. So what happens in viscoelastic materials is you don't see that. You see some initial elastic response, but then it sort of like slowly approaches, right? So if you remember when he dropped like the plate on the ants, they squished it first, and if you were to let that sit there, it would keep on squishing over time until it reached some limit. That's what a viscoelastic material is. And then when you release it, again, it's going to release a little bit at first, and then it's going to slowly decay over time. So it's still in stress and strain. You just have to take into account time. And when you have to take into account time, it's just a new class of materials. These are important because a lot of polymers, and some metals even, if you get them to the right temperature, a lot of polymers are viscoelastic. So when you design around the stress and the strain that you're going to get out of it, you have to take into account time. Okay, let's talk about Poisson's ratio for a minute. Poisson's ratio, you've probably heard about it in physics or somewhere before, but if you take something and you squeeze on it, it's going to get wider, right? It's going to expand. If you pull on something, it's going to get narrower. All that Poisson's ratio is it just defines how much is happening in terms of that, right? When you apply a stress in one direction, what's the strain that occurs in a perpendicular direction, right? So for example, it's the ratio of the strain in the x direction to the strain in the z direction if you're pulling on it in the z direction, right? So it's going to contract or expand in that other direction. They use a negative sign so that Poisson's ratio always is a positive number. And just to have some numbers in mind, it ranges between, say, 1/4 and 1/2 for most materials. So if you have something like rubber, if you squeeze rubber, it's really going to expand out the sides a lot. That will have a Poisson's ratio of 1/2. And if you take other things, I forgot to bring it. I have some cork. If you take cork and you squeeze it, it won't expand at all. Why is that? Why do you think cork won't expand? Any thoughts? What do you think, Jeff? Yeah. Same if you took like a styrofoam or some of these other ones that have lots of air pockets in them, it can sort of collapse so that material doesn't have to expand outwards, right? So those are the two bookends. Cork and rubber are your two ends, and then metals, lots of other polymers, they're all going to be somewhere in between. It typically values between 1/4 and maybe 0.3 or so, okay? What's interesting is that if you know the Young's modulus, which is a relatively easy thing to measure, and you measure the Poisson's ratio, you can calculate the shear modulus with this formula. Again, that only works for isotropic materials. What does isotropic mean? That means when you measure something in one direction, it doesn't matter if you measure it in the other direction, you get the same values. So if you have an isotropic material, you can use this formula to go between Young's modulus, shear modulus, Poisson's ratio. So this is really easy to ask questions about on homeworks or midterms, right? I can give you 2 of these and expect you to find the third. Okay? All right. Okay, we've already talked about this a little bit. When you have your stress versus strain plots, technically the onset of permanent deformation is at point number 2. Point number 2 is when you're now going to introduce permanent deformation. But so that we all agree on something, between 1 and 2 it's still elastic. At 3, I guess, is when it starts to be permanent. And at point 4, when you release that, remember it's got the same slope as it initially had, and you're left with 0.2, we call the stress at point 4 the yield stress, right? Sigma y, yield stress. Okay, the yield point phenomenon. Some materials will transition gradually to this, right? Like in this one, it just sort of gradually curled over to that. Other ones, you might see something unusual happening here. This might be grains sliding past one, there might be something breaking in the material. Some materials just do this. So you have this yield point phenomenon, right, where there can be a discontinuous change in this curve, and then it might continue to rise, okay? You can have a plot that looks like this, where it goes, you've got your yield strength, where something happens, it starts to yield, and then it gets stronger and stronger up to some maximum stress. And then it starts to get, well, it starts to look like it's getting weaker, right? The thought here, and let's ask this, I guess I already kind of gave it away, but true or false, the material is getting harder and stronger up until that peak of that, UTS, and then it gets weaker. So you can discuss with neighbors. Is it getting harder and stronger and then it starts to get weaker? True or false? Okay, we'll let you get answers in another 20 seconds. Okay, true or false? Pretty even split on that one. I think I'll go back and give you points on either one on that one. So it's a bit tricky. It's a bit of a trick question too, right? If you look at this, as you go up here, it actually looks like it's getting slightly weaker because the slope is less here. The instantaneous slope is a little bit less there than it was initially, right? Which says for a given force you're getting more strain, which you'd say that's a weaker material, right? That's fair enough. It can withstand a higher and higher stress, which might tell you it's stronger. But then this really doesn't make sense, right? It starts to get weaker, right? Is what it looks like. So it's actually not getting weaker. What's happening is there is necking. Necking is when you take your sample, right? If you start with sort of a dog bone shaped sample, right? I think I mentioned this in the video on Friday. But as you start to pull on this thing, because this region has a smaller cross-sectional area than this region out here, it has a much higher stress. Because you will recall that stress is equal to the force divided by the cross-sectional area. So if you've got that smaller cross-sectional area in the middle, that's experiencing a much higher stress. They do that so that it intentionally will break in the middle and not where you clamp onto this dog bone. You don't want it to break there. You want it to break within the actual material, not from some defect of the clamps grabbing it, right? What you'll often see though, when you do these testing, especially with polymers or some metals, you'll see that it actually really starts to elongate even further and neck down further right there. So it's that's why they call this localized plastic deformation or localized reduction in cross-sectional area. So that would be your necking. So in that region, because the cross-sectional area got way smaller right there, your stress got much higher. So the problem with these plots when you're plotting stress versus strain is what they're plotting here is engineering stress. Engineering stress is the force divided by the initial cross-sectional area. It doesn't take into account the instantaneous area. If you were to plot the true stress and not the engineering stress, this picture would look different. It would look like the following. I think I've got a spot for it down here. Yeah, if you were to plot it, it would look like the following. So again, we're plotting true stress versus strain. It might go up, but instead of reaching a maximum and starting to go down, it would just keep on going up as opposed to going down, right? Because you take into account the smaller area, and it's getting smaller and smaller, therefore the stress is actually much higher. So where does this come from? True stresses versus true strain. I think this is kind of interesting. Again, it's force over area, and strain, the true stress, is the instantaneous length over L naught. So where do those terms come from? It's kind of interesting. So strain is the change in length delta. So that's just L final minus L initial, right? Over L naught. So the change in strain, we can write it as that. That's delta L over L naught. And if you take instantaneous, you could actually take the summation. You could sum up every tiny part of this, right? Anytime that you see sum, that really in engineering we know we're going to take the integral. So you're going to take the integral of this dl over L, and that's where this natural log of Li over L naught comes from. So on a homework question, if I ask you to solve for the true stress, you could take the instantaneous length, right? Take the natural log of the instantaneous length and divide it by your initial length, L naught, and that will give you your true strain. And if volume is conserved, your total volume is conserved, that allows you to come up with a couple other expressions. Okay, any questions on true stress versus engineering stress or true strain versus engineering strain? Any questions I can answer before we keep going? Yeah, Takar?
Will the true strain ever curve, or will it always just keep going up and down?
It shouldn't, because most materials, we haven't gotten to this yet. When we get to next chapter on deformation mechanisms, we're going to learn that the more you deform something, the harder and stronger it typically gets. It's called work hardening. It's the same reason why a blacksmith, when they're pounding on something, They pound on it, and it gets harder. And every successive hammer blow, it's not deforming as much. Part of that is because it's getting cooler, and part of that is because you're work hardening it, right? So they have to heat it back up, they pull it back out, and then they pound on it again. But basically, if you're a blacksmith, the first couple hammer blows when it comes out of the furnace, you get big changes, and then you get small changes after that, okay? So most materials, it should keep going up. It should keep getting harder and stronger. There's probably some exceptions to that. Again, here's an example of necking. This was the initial unstressed bar. When you start to stress it, the distance between these, I don't know if that was like a centimeter or whatever it was, but that distance right there has gotten longer. So overall, the whole thing has gotten longer, but then something happened right there where some really dramatic localized deformation occurs, and that's evidence of necking, right? Okay. We forgot to do our learning objectives. So let's talk about what else we want to cover today. We're going to talk about ductility a little bit more. We're going to talk about what happens to your Young's modulus when you introduce things like porosity. Okay, you went from a pure metal to one that has tiny little pores in it. What does that do? We'll talk about some non-Newtonian viscoelastic materials. This is most polymers. And if we have time, we're going to talk about the glassy transition and hardness, and maybe even Weibull modulus. We'll start that today. Okay, ductility. When we talk about ductility of materials, what we're really measuring is the change, is basically how much plastic deformation can something take, right? Whether that's reduction in cross-sectional area or elongation, you could calculate it either way, right? So percent elongation is going to be your L final minus your L initial over your L naught, right? So this is just strain times 100%. That's your percent elongation. You could also do it with reduction in area, right? If you pull on something and the area starts to shrink, that's another way to calculate ductility. So either of these are appropriate measures of ductility, right? Okay, then you've got brittle and ductile materials. If you have a material that's ductile, then you have the possibility of plastic deformation, which is happening over that region of the curve. Remember, an elastic material, none of this from here to here is plastic deformation. That's all elastic, right? And a brittle material, you might be able to load it up to a high value, but it's not ever going to start to bend, right? A plate, for example, a dinner plate, I can pull on that, and eventually it'll break, but it's probably never going to bend an appreciable amount because ceramics aren't plastically, they don't deform plastically really. They tend to just fracture instead. Now the area under this curve is equal to the absorbed energy during loading, right? Now how do we get energy out of that? Again, we're plotting stress versus strain. Strain has no units. Stress has the units of, say, something like pascals. So if you take the area under the curve, what should the units be? Remember this from like physics? If you have like distance versus time, you would multiply the two, it'd be distance time, would be the area under the curve. So here, the area under the curve is just pascals. And yet I've said that it's equal to absorbed energy. So how does that work? Well, let's write this out. 1 megapascal, that's equal to 1 times 10 to the 6th newtons per square meter. And that is, by definition, equal to 1 times 10 to the 6th joules per meter cubed, right? So joules, there's our energy term, right? So what it's really saying is that if you took into account the entire volume of your sample that was the stress was being applied to, there will be some amount of energy being stored in that entire volume, that whole meter cubed of your sample, right? So that's how you get this energy stored in your material, right? So if you want a material that's going to absorb lots and lots of energy, you want to maximize the area under this curve, okay? Another thing is you've got resilience. Resilience is one of our clicker questions today. Resilience is the area stored under the elastic part of this curve only, right? So this pink material, the red material and the pink area under the curve, that's all happening under the elastic, right? So a spring is a perfect example of this. A spring, you want to be able to deform your spring and have it go back to where it was, right? So a spring is something that's going to absorb energy but not permanently deform. So you want it to have a high modulus of resilience, right? Whereas if you have something, well, give me an application. Where do you want an application where it has a huge area absorbed during fracture? Any thoughts? Yeah, Jeff? Car crash, right? Exactly. You want to absorb as much energy as possible for a given amount of strain, basically, right? What else? Anything else? So bulletproof vests. We'll show you how engineers have mimicked what nature does in doing that. You want to absorb energy, right? Okay. So here's some examples of high toughness materials. Again, the area under this entire curve is the toughness, and the area just under the elastic region is your modulus of resilience. So materials that have high toughness are often things that are layered structures. And evolution has made some of these things. So birds, when they eat tiny like sea mollusks, right, they'll grab that thing, pull it off the rock, fly high up in the air and drop it, and the shell will break and they'll be able to eat that delicious slimy sea creature on the inside. So these delicious slimy sea creatures have evolved to become tougher and tougher so that when they get dropped, they don't break, right? The way they do though is they have calcium carbonate, which is a ceramic, which is brittle, which is not great for toughness, right? It's good for hardness, but it's not great for toughness. But then they'll have this sort of biopolymer, this collagen layer between them. And by forming layers like this, what happens is that when a crack impinges on this material, it's going to see sort of like scattering events. That crack won't go straight through it. It's going to get deflected and therefore absorb a lot of energy, right? So people that design bulletproof vests have taken lessons from this. They make hard layers. They put sort of really elastic layers between them that are going to absorb energy than the hard layer. And by making layered materials like that, you can make a material that absorbs a ton of energy, okay? Okay, let's talk about when you take the load off after you've applied something. So you load it up until this point, it's linear and it's elastic. At this point, you're starting to get plastic deformation. You take it to that point, and then you take the load off, right? In your Instron, you move the crosshead back up, and you relax it back to nothing. The load will drop to 0. It will recover a little bit of its strain, the elastic amount. And then if you were to pick that thing up where you started from, it's just going to load right back up, just like this drawing shows, and pick up basically where it started from, okay? So many materials have that can occur. Will a stress versus strain curve look the same for a material if it's compressed instead of pulled apart? This is actually not a clicker question. This is just a group one. So you tell me, ask your neighbor, is it going to look the same if you pull it apart versus you squeezing it? Okay, what do we think? Is it the same? Is it different? And what's your rationale behind your thought? Anybody want to give this a shot? Yeah.
So the curves will look different because if you're compressing the material, necking won't occur, so you won't have that like drop off.
Yeah, you probably won't see that whole, above the ultimate tensile stress. You probably won't see that. I agree. Anything else that might look different? I think that's the main one. Yeah, Spencer?
Isn't it like on the Young's modulus, as you push it in, it goes infinitely stronger, the repulsive force? So
yeah, that's the right way to think about it, right? So remember, again, he's thinking of in terms of force versus your inner atomic separation. Or let's do energy for a minute. Energy, it drops really steeply, and then most materials are asymmetric. So basically, it's easier to pull them apart than it is to squeeze them together, right? So exactly right. So you should get a slightly different Young's modulus, right? Technically speaking, that you'd expect something slightly different. Or you shouldn't be surprised if you do see something slightly different. So oftentimes you'll see things reported with very specific scenarios, right? They'll do, again, on Friday we talked about ASTMs, which are specific ways to test things. And you'd want to look at the ASTM that most closely simulates your use environment, right? Another reason is that things just break under tension easier than compression. So you can achieve really high loads, right, under compression, but that's not maybe necessarily the same as what's going to happen when you try and load it under tension. It might break a lot lower. Okay, what happens when you do, let's see, first off, how do we test ceramics? When you test ceramics, if this was made out of ceramic and I grabbed onto it with some like vice grips, the odds of it breaking when I grab onto it are pretty high. Like if you took some vice grips and grabbed your dinner plate, it's just going to fracture, right? Because it can't stand any plastic deformation. So right where the teeth bite into it, that's plastic deformation. It's probably just going to fracture, right? So how do you test those things? You can try and grab onto it like a really smooth surface, but it's still just not great if you're going to try and pull this thing. So instead what they do is they tend to do bend testing. Bend testing with ceramics is a much better way to go because, again, you'll take two things on the bottom, one on the top. These push up, this pushes down. You're going to slowly bend your sample, right? Just like this pen, I'm going to slowly be able to bend it. And I can do 4-point bending like you see here. 2 thumbs on the bottom, 2 fingers on the top like that. Or you could do just 3-point bending like that. Either is acceptable, and they do both of them, but there are some differences between them. Okay? The reason why we like this is because if you do this, you're going to see that there is tension right there, and there's going to be compression right there, right? So that'll be the point of fracture on the bottom. That's because that's under tension. Ceramics break under tension way easier than under compression. So that crack is going to grow from the bottom up, right? So this is not technically like yield strength, like a tensile yield strength. It's a different thing. We call this the modulus of rupture, MOR, sometimes they'll abbreviate it as. And you can calculate what that modulus of rupture would be from the geometry of your sample, the separation distance between these points, right? This distance L matters. So that all that geometry can be plugged in, you can figure out what your modulus of rupture is, and that's a pretty good substitute for your tensile strength. And it's certainly a lot easier to measure for ceramics. So the question now is, should it be the same for 3-point versus 4-point bending? So what do you think? Will bend strength be higher for 3-point or 4-point bending? Which one will give you the higher strength? 3-point bending or 4-point bending? Okay, who feels brave? Any thoughts? Yeah, Rob, what do you think?
I figure that I'm probably going to break sooner under 3-point bending because the force is distributed over a smaller area.
Okay, let's clarify terms a little bit. Let's say this is the thing I'm wanting to break, and in both cases, my outer span is at the very edges, and in one case, in 4-point, my thumbs are sort of, they cut it into thirds, right? And the 3-point bending, it's right in the middle. But the outer span is the same in both cases. So is 3-point bending or 4-point higher? Anybody want to give a shot at this? And what's your rationale? Yeah, what do you think, Griffin?
4-point will be a higher bend strength because you have more balance forces pressing on the whole plate, where 3-point bending, you're having one force in the middle that's going to be able to...
It's a good guess. It's not right. It's a good guess, though. What do you think?
I would say 4-point bending, 3-point bending, you have a larger moment.
Yeah, so that's the right way to think of it. If you've taken statics yet, who's taken statics in here already? Yeah, so when you look at your bending moment, how do you calculate the bending moment, right? So if you take a look at this, you've got your forces. You can do your force diagram on this thing, okay? If you look at the bending moment, they can both reach the same absolute value for your bending moment, but because you're 4-point bending, it's going to increase until that point, and it's going to be flat all across here. Then you have this whole region from here, oh gosh, this is the worst bracket I've ever done. Sorry, hold that thought. From here until here, all of that region, that's all experiencing a maximum bending moment, right? Whereas only a maximum bending moment is occurring at one spot, the 3-point bend. Therefore, a 3-point bending test will give you a higher strength because you could have a critical flaw in your sample right here, right? That might be where your biggest flaw is, but it's not experiencing the full bending moment. In this case, that critical flaw that's right there, it's experiencing your bending moment, right? So what we say is there's a difference in the effective area under which you experience this maximum bending moment. So if you took the exact same samples, all things equal, you tested some of them 3-point bending, some of them 4-point bending, your 3-point will show you a higher strength. But that's only because you're not having this well-distributed maximum bending moment. It's only happening at one plane in your sample. Rosa?
What exactly is a bending moment?
So think of it like a torque arm. That's maybe a good way to think of it. It's a force multiplied by a distance. There's more to it than that. And if you haven't taken statics, don't worry about it. You don't need it for this class. But think of it, in this class, you can think the bending moment is going to it's going to be what causes rupture. The larger the bending moment, think of it like a higher stress that's locally present. And basically here, your stress is ramping up and it reaches a max and then goes down. Here it ramps up quickly and it stays at a max and then goes down. Yeah?
So is the bend strength the amount of force that it takes to break the sample, or how much the sample can take?
So the modulus of rupture, or sometimes the flexural strength, it's just calculated like this, right? It takes into account the force, it takes into account the span, it takes into account the sample geometry, B and D, the thickness and the height. And that stress is when your sample breaks, okay? This is commonly used for ceramics because we can't grab onto them like a polymer or a metal very easily because they would just break. Okay, so that's 3- and 4-point bending.
Question?
Yeah.
Could you just remind us the difference between stress and strain?
The difference between stress and strain, so if you take a sample and you apply, say, a compressive stress on it, meaning it's happening perpendicular to the faces of your material, you will cause this material to change its initial length. In this case, it's going to get smaller, right? And it's actually going to, its final shape might look something like this. It's going to get a little bit fatter, because the Poisson's ratio is not 0. If this was cork, it would not get fatter, right? But it's going to get a little bit shorter. So its change in length, the delta L over its L naught, that's equal to strain, whereas stress is equal to the force divided by whatever the cross-sectional area of this component was. Okay? Okay, you can also have ceramics that aren't fully dense. In fact, most ceramics, when you make them, it's actually extremely difficult to get them fully dense. You typically start out with little tiny particles and you cause these to sinter together or agglomerate together. And in that process, it's hard to get rid of all the pores. So there's some sweet videos. Again, scientists in the 50s loved to do bubble rafts. And here's them showing how bubble rafts can simulate ceramics when you sinter them. So they started out with things that were separated a little bit. Then they release them from the cups that are underneath the water, and they allow them to sinter together. And if you look at this, there's regions at the intersections of these grains where there's that little pore left over, right? So the exact same thing happens with ceramics. Now we're not talking about bubbles on the surface of liquid. You're talking about little globs of dirt, right? Little particles. You pack them together, you throw them in a furnace, and those particles start to merge together. But getting them completely merged so there's no spaces in between is really tough to do. All right, let's watch another one. I think they've got another one. So they're going to keep growing, and they'll eventually, if everything's perfect, they'll grow together. Let's see, I think they have another one here. So again, when they release it, these things slowly start to grow together. The fact is, when you order engineering materials that are ceramics, whether it's alumina or whatever else, you probably will have some porosity left over. So an engineer will ask, how will that porosity influence my properties, right? Like, say, modulus. And there are some theoretical ideas of how it works, but more useful for you are some analytical expressions that'll just allow you to calculate it. So here's one analytical expression. The modulus that you will observe is equal to the modulus of the fully dense material multiplied by this factor that has P in it, where P is your porosity, right? So that's going to be percent porosity. So if you have 10% porosity, you plug in, you might plug in 0.1 actually. I'll have to double check that. Okay? Same thing with your flexural strength. Your flexural strength for a porous material is going to be less than the fully dense material. The pores act as stress concentrators for the same reasons that we learned about before. It's going to reduce your strength and reduce your modulus. Okay. Other questions on ceramics before we move to polymers? Okay, you've got polymers, and at the beginning of last chapter or something, we showed you with the banana that if you pull it very quickly, you can get a brittle fracture, and if you pull it slowly, you get plastic deformation. And the same thing can happen with temperature. So you have two things you have to consider: the strain rate, the rate at which you're going to apply the load, and the temperature. And both of those can make it go anywhere from like a rubber, like this thing looks like a rubber, to something that looks a lot like a ceramic, right? Just by controlling the temperature and the strain rate. And that's not just like a cartoon. You can actually see this. Here's real data. So this is PMMA, I think. What is this? Yeah, polymethyl methacrylate. Again, if you do this at high temperatures, at 60 degrees Celsius, it looks like rubber, basically. If you do this at 4 degrees Celsius, it looks like a ceramic. Just like wildly different behavior depending on the strain rate and the temperature. So if they plotted this again with strain rate, you'd see similar behavior. Fast strain rates and slow strain rates. And just to remind us what's happening, when you start to, let's say, stretch a polymer, it started out as a bowl of spaghetti where the noodles were not aligned, they were just random. And when you start to pull on this thing and plastically deform it so it's stretching, what you're typically seeing is these things are starting to line up. They start to line up more and more and more. And so it actually starts to crystallize. It starts to look more like a crystalline polymer as you're stretching this thing. Yeah?
You see that behavior in other materials, not just polymer? The strain rate and the temperature.
Oh yeah. Metals, for example, yeah, absolutely. It's more pronounced in polymers because they melt at a low temperature, and so overcoming that, the temperature needed for them to overcome their van der Waals bonding is low compared to metals. But yeah, you absolutely will see that in metals and ceramics, right? That's why a couple chapters ago we showed you like the picture like the Liberty ship, which in cold water that metal became very brittle when it was expected to be pretty ductile. It underwent a ductile brittle transition, just like you saw there. Okay, viscoelastic, we've already talked about this, that an elastic material, when you apply a stress instantaneous like that, you get an instantaneous elastic response. But a viscoelastic material is one like the dark line, where it gets this initial elastic part, and then it's going to rise slowly, right? How about this? Maybe turn to a neighbor and describe, if both temperature and strain rate can influence the mechanical properties of a polymer, how do you decouple them for study? What would you do? Okay, what do we do? How would you go ahead and report this? Yeah, is it John?
Yeah, you would probably fix one variable and vary the other.
Yes, as our notes have happily told us, right? Fix one variable and vary the other. That's exactly right. So when you do these, let's say pick one temperature, right? Everything is going to happen at room temperature, and you're going to try a bunch of different strain rates. Then you heat it up a little bit more, and you do a bunch of those, right? So by fixing one and then varying the other, you can actually generate an entire what's called stress relaxation curve. So here's what they look like. All of these, you're looking here at the stress relaxation modulus, okay? And they're plotting that at different temperatures, and you see these different things happening. You could take that and you could plot them as a function of time and generate what's called a glassy transition curve, right? So up here, something that will happen at a short period, let's see. After short periods of time, it looks elastic, right? At long periods of time, it starts to look like it's going to flow. So this is the glassy transition curve. Let's show it against temperature, it's a little bit better. The glassy transition curve, so this might be your modulus, right? As higher temperatures, it's going to start to look like a liquid, and at lower temperatures, it's going to look like a glass. And there's this region in between where it goes through what's called the rubbery plateau. So this temperature right here, where it starts to transition, that is called the glassy transition temperature. So that's a really important thing for you to know if you're going to work with polymers. You'd like to look up on the spec sheet, what's my glassy transition temperature? Because you know if you keep it below the glassy transition temperature, you can model this like as if it was a ceramic in some ways, right? You're going to see an elastic response. You won't see this time-dependent response. It'll be elastic. But if you go above it, it's now going to start to look more like leather, then rubber, and eventually maybe like a liquid, right? So honey, again, honey in winter is up here. It's a glass. Honey in summer, especially out of the microwave, is going to be a liquid, and it can be everywhere in between, right? So many polymers, I'd say most of them, they have a glassy transition curve, and so you simply need to define the glassy transition temperature. The glassy transition temperature, by definition, totally arbitrary, we picked this, but by definition we said when the viscosity is 10 to the 12 Pascal seconds, that's a unit of viscosity, that's the glassy transition temperature, right? And it was just arbitrary that they selected that. So again, below the glassy transition temperature, imagine that the chains are frozen. They're not going to move past one another very easily. And above it, they're free to move in significant ways. So if you were going to sketch, let's do this real quick. Let's sketch this. Maybe this will be the last thing we do today, actually. If you were to plot Young's modulus versus temperature for 4 different materials, a crystalline isotactic material, a cross-linked atactic material, and a low molecular weight versus a high molecular weight atactic material. So these are all the polymer. The only difference is that the side group is all on one side with isotactic. It's random, but it's cross-linked, or it's not cross-linked and it's low molecular weight versus high molecular weight. How will this glassy transition curve look for these 4 materials? Take a shot at sketching that, and we'll probably end on that note. Okay, if that's our generic shape, how should we modify it for some of these polymers? Any thoughts? What about the crystalline isotactic? How should this thing look different for crystalline isotactic, and what's your rationale? What do you think, Brandon?
Since you said that as it polymer next it gets closer to the strain point, it gets more crystalline appearance. Something that's already crystalline is likely to behave more like a ceramic or a metal.
Yeah, the more crystalline it is, then again, if that's our polymers that are lined up more, then they have more regions of overlap between them. And that causes you to have higher bonding between those chains, right? Your van der Waals forces are higher. So it would look maybe something like this. Its glassy transition temperature is gonna be shifted to higher temperatures, right? Because it's bound together more tightly. It will eventually go through this rubbery plateau, and then it's going to eventually melt, right? Because we haven't done anything to make it not melt. What if you made something not melt? How do you achieve that? You cross-link it, right? So the material that's cross-linked, it might look like this, but it'll just keep on going out until it just burns in it. no longer there, right? So the cross-linked material will never flow. A tire, like a car tire, if you heat it up, it won't melt and flow. It just burns, right? So it's never going to get to that liquid part. It will become increasingly soft, right? And then you've got low and high molecular weight. So the low molecular weight might flow at a much sooner point than your high one, right? So this would be like the low molecular weight. This would be high molecular weight. This would be cross-linked. And this would be crystalline. Okay, we'll pick up here next time. Or yeah, question, Barson?
What if you heat it up in a vacuum, though?
What if you heat it up in a vacuum? Which one?
The tire.
The tire?
Yeah.
It will melt then. Yeah. Yeah, it'll melt at some point.